Thank you for joining us for today's Wurth Elektronik and Texas Instruments Power Seminar, USB Type-C and USB Power Delivery Made Easy. Today's presenters are Eric Beljars, Product Marketing Engineer with Texas Instruments, and Apurva Engel, Product Definition Engineer with Wurth Elektronik. As a reminder, you will automatically receive the recorded presentation and PDF of the slides within the following week. Register for other online events at www.we-online.com/events. If you have questions throughout the presentation, please write them in the questions box and our presenters will answer them at the end. Thank you for joining us for today's Power Seminar.
Hello everyone, my name is Apurva and I'm a Product Definition Engineer with Wurth Electronics. Today the topic for our online seminar is Type-C USB Made Easy. This presentation is a joint collaboration between Wurth Electronics and Texas Instruments. So I would like to thank the team of TI for their great support, and together we hope to make this USB Type-C topic easier for you to understand. In this topic, I'll focus in the first half of the presentation on USB Type-C as a technology, and I'll also discuss the Type-C connectors and cables in little more detail. So our agenda today will cover little history of USB connectors, then why specifically USB Type-C is getting so much of popularity and what are the benefits of it. Then we will look into specific connector designs for Type-C receptacle and Type-C plug. Moving on to potential issues that we face while using these connectors and what could be the easy solution fixes for that. And lastly, we'll conclude with a quick summary of all those points. Now, the history of USB connectors goes way back to 1994, when a group of 7 major companies started working on Universal Serial Bus. The goal behind this was to make the connection easier between the external devices and the PCs by replacing multitude of connectors at the back of this PC. Now, the USB was expected to make the existing interfaces more user-friendly, simplify software configurations to the devices that are connected, as well as permit greater data transfer rate between these devices. The original USB 1.0 specification, which were introduced in 1996, defined data transfer rates of 1.5 megabits per second at low speed and 12 megabits per second at full speed. Now, in an initiative to develop higher data transfer rates, USB 2.0 specs were released in the year 2000, which helped to achieve a speed of 480 megabits per second, which was 40 times higher than USB 1.0. Now, USB 3.0 came into picture, of course, to increase the data transfer rate even further, but also to decrease the power consumption, increase power output, and be backward compatible with USB 2.0. Now, the speed that we could achieve was in gigabits range. In 2013, with USB 3.1, we now have 10 gigabits per second transfer rate. And as recent as 2019, with the capability of power delivery, we can achieve super speed till 40 gigabits per second. The USB Type-C is the first connector with which we can support power in both ways. So we can use this connector for power transfer, to stream videos, data transfer, or charging our electronic devices, as well as connecting some peripherals such as keyboard and the mouse. Now let's see what's new in USB Type-C. We have added 2 configuration channels, CC1 and CC2. Now these channels are important because with this, we can plug the USB Type-C both ways and we don't have any limit on the entry positions. The configuration channel detects when you connect the USB ports. It resolves the cable orientation and determines which connection goes to which device. It also establishes a connection, like which connection is DSP, which is downstream facing port, also known as the source, and which of the connection is UFP, which is upstream facing port, also known as sink. Next, it can also discover we are operating the connector in current mode, or if we are using it in some advanced mode such as power delivery or working it in optional alternate or accessory modes. So with the help of these configuration channels, we can identify how the connector is working. Besides current mode operation, USB Type-C also has certain extended capabilities, starting with USB power delivery mode, which is a single wire communication protocol over CC line. Now with PD, we can negotiate the power up to 100 watts when compared to just 15 watts under standard operation. Next one is alternate mode. With this mode, USB Type-C interface can be used for some non-USB cases as well. And lastly, we have role flexibility. So by default, the host is considered as the power source and the end device is referred to as power sink. But with USB and USB PD, we have the capability to switch those two and both can play both the roles. Now in product overview, we can see the Type-C receptacle on the left and Type-C plug on the right here, which can be connected using a USB Type-C cable. Now in this cable, the center part is all connected with data line, whereas the edges of the cable all represent the power line. And in the side cross view of a receptacle on the left and plug is here on the right. Now when we are intersecting these two, we can see something like a picture below. Now in this picture, we notice that the top and the bottom edge of the connector is nothing but the shielding that we have put inside the connector. But the center part is the one which is our actual defined end of contact. And this defined end of contact is very important and very critical because this is the part which will guarantee the definition process of our signal communication. In this overview, we can see which color is linked with standards of connector. For example, the red one here represents USB 2.0, whereas with USB 3.0, we have the blue transmission and receiving pins. And with USB 3.1, we have additional configuration channels, CC1 and CC2, and also SDU1 and SDU2. Now, what these two channels are doing is that they are making it configurable for low-speed data lines if we are using this connector for alternate mode, making this connector a very, very customizable one and a very flexible one to change with different type of operation mode. And this is why we can also use this type of connector in other applications such as audio. Now, under electrical ratings for Type-C receptacle, we can see that together the 4 power pins are rated for 5 amps. Other pins are rated for 1/4 amps with a working voltage of 20 volts DC, and the maximum voltage that they can withstand is 100 volts. With the pitch spacing in between the 2 pins being very, very small as 0.5 millimeter, the interface should be capable enough to handle any possible shorts between these pins. As you can see in the picture, the distance between 2 adjacent pins is really tiny, and we need to make sure while inserting or detaching the connector that we are not creating any accidental short. On the same lines, we have these soldering examples that could help us with connecting the connector in an efficient way on the board. If you take a look at the first picture here, it is considered soldering without any defects. As we can see, the pins are soldered very properly. We don't have any smudges or outlines that we can see. Compared to something like a cold solder in the second picture, where the pins are laid pretty perfectly, but we still see some black marks around certain pins. Now, these black marks or these black shadows, they represent that we have some air trapped around the pins. And we'll see in the later slides that with the presence of air in between these pins, we have a possibility of creating an accidental short, which could potentially damage the connector. And lastly, the last picture is for a simple hand soldering, which uses no machines, just soldered by a solder gun. This type of soldering is only good if you're doing some initial testing or prototyping, but definitely it's not recommended for longer durations. There are two simple ways to see if the connector is soldered properly on the board. One is AOI, which is automated optic inspection, or the second one is a simple X-ray. Now, with the help of X-ray, we can see in the first picture, we can just see the outline of these pins, and everything is very clearly marked. We don't see any shadows or any smudges here, compared to something on the bottom where although the pins are very well laid out, but we still have these white marks, which are representing presence of air in the connector. And we just need to make sure that we improve this type of solder if we are putting it finally on the board. This is a final product representation of the USB Type-C receptacle and the plug. Point to note here is that since we know Type-C has no orientation requirements, even if we flip this plug and try to use it with the receptacle, it will just perform the same and we'll have the same success as we do if we flip it other way around. So there is no need to worry about the orientation. Similar to the receptacle, we also have a pin layout for Type-C plug. And if you notice here, it is a 22-pin plug instead of a 24-pin plug as we saw for the receptacle. The B6 and B7 pins are missing in the plug. Now, if we implement these B6 and B7 pins with a differential pair D- and D+, we are essentially creating a short, and there might not be any data transferred through the connector. But having said that, we still have like newer USB Type-C plugs which are coming out with 24 pins. But in that case, a small multiplexer IC is used behind the connector, which helps us to divide the signal, making it possible to use the connector with all the 24 pins on both the sides. This is a small picture to show few critical add-ons on the connector, such as retention springs and flanges. These are not the mandatory part, but it is always recommended to have high retention. High retention is ideal for applications where connection reliability is very, very critical, or when the strain on the connection may be subject to higher than average force. And to observe and sustain that force, we need these retention springs, so that even if we have like a small jerk while inserting or detaching the connector, it won't get damaged. Similar to receptacle, it is also very important that we solder the plug connector very, very carefully. Now, if you see the top side and the bottom side view, the pins are again laid out very close to each other, and we just don't want to create an accidental short just by putting on too much of a solder and getting it mixed with the adjacent pin. Or we don't even want to put very, very less solder and leave one pin hanging, which would just create a loose connection. In the next few slides, we will go through some of the potential issues or potential mistakes that we make while using these connectors. First one is a very simple mechanical twist. So here you can see that we are trying to connect the receptacle to our device. And when we try to detach this connector, and if we don't do it in a straight line, we have a chance of creating an angle in between the pins. Now, what this angle will do is it could create a short between the voltage lines or the configuration channels, or even with the data lines. And this could potentially either damage the device or damage the connector or the cable itself. Next potential failure is presence of debris or water in between the pins. Again, as we saw that the connector is small itself and the pitch of the pin is even smaller, if we have any air or dust or water present in between, again, we have a very likely chance of creating a short in between the voltage lines and the data lines, damaging our device. And lastly, use of non-compliant cables could also cause a lot of potential issues. Now, let's say we are not even using power delivery feature and just charging at normal 5 volts and 500 milliamps. Even under these normal circumstances, the non-compliant cables can take an output as high as 20 volts, and this could potentially destroy our end device. Based on the survey on USB Type-C cables, almost 28% of the cables in market are non-compliant. All the major companies have put restrictions on selling these cables. There is a very good chance that we might end up purchasing it if we are not just careful enough while buying it. One of the popular and standardized cables these days are cables with E-markers on them. Now, what does that exactly mean is that we have a very simple USB PD controller situated inside the cable. Now, this type of cable can help us respond to USB commands from the source. It can also provide other characteristics such as current carrying capability, provide vendor information, as well as do performance identification. Now, E-markers are always recommended, but particularly needed when we have an application that is supporting more than 3 amps of current, or Type-C fully featured cable with USB 3.1, or if we are operating under alternate mode signaling, it is always recommended to have E-marker cables. And finally, we can summarize the points that are making USB Type-C such a convenient option. And this is the type of connector which is meant to replace most of the other connectors, simply by starting with the fact that it is so much more convenient to use compared to a lot of older connectors. Although being smaller than micro B connector, it is still 10 times more robust mechanically. It is reversible and plugs in with any orientation. Additionally, both ends of the cable have the same connector, which makes the cable itself reversible. And most of us must have faced difficulty when we are plugging in something like a Type A connector, where orientation is such a critical part, and we just end up flipping the connector 2-3 times before getting it right, especially when we are doing it in a rush. Now, Type-C connector is robust in this aspect as well, because it is designed for 10,000 insertions when compared to 5,000 in mini USB and only 1,500 on standard USB Type A connector. So this allows us to plug a Type-C connector and plug in out more number of times. In Type-C, we have the spring contacts on the cable and not on the socket itself. So if we need any kind of replacement, it is much more easier to replace just the cable rather than changing the socket. The cable has 5 data pair lines, which allows speed up to 20 gigabits per second under USB 3.2 and up to 40 gigabits per second under USB 4.0. And it still can be backward compatible for lower speeds. Next big advantage with Type-C is the delivery of more power. This is the first connector which can support power delivery between 7.5 to 100 watts. And lastly, it can support multiple data protocols with alternate mode, as well as a lot of video protocols. And that is what makes this connector so much versatile to use. And it will also be able to support other future protocols which are coming in the market. So having said that, we conclude the part of USB Type-C as a technology and the passive that we use on the connector side. And now I would like to hand over the presentation to Eric, who will go into a little bit more details about the USB Type-C and PD controllers from TI. Thank you.
Thank you, Apoorva, for the introduction. My name is Eric Beljars. I'm a product marketing engineer for Texas Instruments, focusing on our USB Type-C and PD controllers. So briefly, I'll go through the agenda here of what we're planning to cover in this webinar. So initially, we'll talk through some of the USB Type-C and PD technology. We'll give a brief overview through that. I'll give a quick highlight on TI's USB PD products. Then we'll go into some of the power architectures we use on USB Type-C and PD ports. And then we'll highlight one of our EVMs, which is the USB-C PD Duo EVM. And finally, we'll finish by highlighting TI's USB Type-C PD and power path protection. So briefly here, I'll give a quick overview on the technology. So we can see that we went from USB Type-A connectors to micro B connectors to now Type-C connectors. So with USB Type-A, both the power roll and data roll were tied together on that connector. So a USB Type-A connector is typically a power source as well as a data DFP. So DFP stands for downstream facing port. That means that the USB type A port is the controller of the data for that connection. The micro B port was typically used for sync applications or data upstream facing port, UFP connections. So with that, the micro B connector was typically used on older smartphones where you would plug into a notebook and the notebook would control that data connection as well as provide power to the micro B port on the phone. With Type C, the data roll and power roll can be mixed and matched and swapped together. So you can have a power source with a UFP or a power sync with a DFP. The data roll and power rolls can swap, and you can have any combination of the two. So USB Type C is a new connector. If we're just referring to the connector itself, that means that we can support the 5 volts up to 3 amps. So that is standard Type C protocol. If we want to support more power than those 15 watts, or we need to support video or a specific alternate mode, then a power delivery or PD controller is required. There's a handy video linked here as well that goes into more details between the difference of Type C and power delivery. Additionally, on the screen here, we can see several applications that we've seen using Type C or PD in their systems. I'll briefly go into the example here of the laptop, where the laptop is using almost all the functions that are possible on the Type C PD port. So the laptop can both be charged from Type C PD. In that case, it is the power sync, or it can provide power to downstream devices such as flash drives or mobile phones. In that case, the laptop is the downstream facing port and the source of power. Additionally, the laptop can provide video when you connect it to a monitor, so that's done through the use of an alternate mode. Here we'll briefly go through the TI's portfolio of USB products. So although the Type C connector is the latest protocol and the newest connector, we also have some that control USB Type A ports. On the USB Type A port, it's common to see the B being used. This is a legacy battery charging protocol that uses the USB 2 D+ and D- lines to negotiate the power and complete the power handshake from the source to the sync device. The TI Type A products, such as the TPS2547, integrate the source power path so that you can manage the current going through the path, and there's also integrated current protection in case the sync device connected to the Type A port draws more current than it should. The TPS2547 will automatically limit the current and protect it against such non-compliant devices. Next, we'll go through our portfolio of standard Type C only devices. So like I was mentioning on the previous slide, these are the devices that just support the Type C connector on its own. They can support up to the 5 volt, 3 amp use case, so the power source, and of course they're using the fully bidirectional and orientation agnostic Type C connector. So with this, we recommend using the TPS25810, which can support the 900 milliamps, 1.5 amp, and also 3 amp Type C connections. Additionally, these parts also have the source power path integrated for the same use case as with the Type A ports. If there's a non-compliant device connected or something that draws more current than it should, the power path will automatically limit the current and protect against such devices. In this case, for the Type C only use case, the CC lines, the configuration channel, is used to control how much power is being provided and what's the negotiated current level. Finally, if a full power delivery system is needed, so you need to support more than 15 watts, or you want to add an alternate mode such as DisplayPort or Thunderbolt, then we recommend using a fully featured PD controller like the TPS65987D or TPS65988. I'll go into some more details on these parts in the coming slides, but at a high level, you can see that the TPS65987 has both the source and sync power path integrated. This is important for Type C and power delivery systems since you can do both sourcing and syncing of power on that same port. However, typically, you don't want that power to go or come from the same places. An example of this would be if you're using this first power path to source power, you would connect this line here to your DC to DC supply, which generates your sourcing voltage. However, if you're syncing, you can use this second power path here and connect this line here to your battery charger or your other system rail where you want your syncing power to go. The TPS65987 supports the full PD spec, as well as supporting the legacy BC 1.2 protocol. So in case you do plug an older legacy device into this port as well, it will still charge at the highest current possible. Next, we have another portfolio of power paths, so USB Type-C power paths only. We have the TPS 66120 and TPS 66020. These are used in case you need additional power paths in your system. The TPS 66120 is a high voltage sync only power path, while the TPS 66020 includes both a 5-volt source power path as well as a high voltage sync power path. Here's an overview of the hero products for TI's USB offering. As mentioned on the previous slide, the TPS 65988 and TPS 65987D are our recommended PD controllers. The TPS 65988 is actually a dual port controller, so you can control up to 2 Type-C ports with this one chip, while the TPS 65987D is a single port controller, so 1 Type-C port. We've seen customers that require 1 Type-C port and 1 Type-A port in their system, and this can also be achieved by using the TPS 65988, as you can use the second port to control a USB Type-A port and the first port to control a USB Type-C PD port. So both the 65988 and 65987D are PD controllers, so you can do up to 100 watts with DisplayPort video and other alternate modes. Additionally, they integrate the internal power switch, so you have your fully managed power paths within the device itself. The main benefits of these solutions is that it's a smaller size, a higher integration, and also higher performance for the power paths and protection. So one of the other benefits I want to highlight is that power FETs are integrated here, so there's no need to source external power paths, which can become a sourcing nightmare at some points in time. Next, I'll highlight what we know as our protection devices here. So the TPD 6S300A, this is a USB Type-C protection chip, which will protect against events where some of your pins can short to one another. So if B-bus shorts to the CC line or the SPU line, you can damage some of the circuitry that's on those pins. So the TPD 6S300A is a protection chip that's placed in between the Type-C connector and the PD controller to protect the system from such events. For Type-C only, so standard 15 watts, the TPS 25A10 is the recommended part. This controls just the standard USB Type-C port and also has the integrated power switch. Finally, for a USB Type-A port, we have the TPS 2546. This one supports the BC 1.2 protocol to charge your legacy devices at the highest possible current. This device has been tested with over 100 plus BC 1.2 legacy devices. Finally, we have our portfolio of power paths, which is the TPS 66020 and the TPS 66120. With that, the TPS 66020 integrates both the sync and source load switch. So there's a high voltage sync load switch, as well as a 5-volt only source load switch in this part. This pairs with any PD controller on the market and will still allow you to have the benefits of the TI power path performance and protection in your system. On the other hand, the TPS 66120 is a sync only load switch, so it just has the high voltage sync load switch. So no matter what your USB requirements are, there's a product here that could meet your needs. Going into some of the power path architectures for USB Type-C and PD, I mentioned earlier how you will need a separate power path to control both your sync and source power. So with that, the TPS 65987D is a single port controller and it has dual 100 watt power paths. So you have 2 internal power paths that can support up to 20 volts at 5 amps. So with this device, you can see that you can support sourcing current of up to 5 amps at 20 volts, as well as syncing current at up to 5 amps at 20 volts. So you can have a fully bidirectional power source and sync that can support up to 100 watts of power in either direction. Additionally, the VCON power paths are also integrated in this device, and it also offers support for external source and sync power paths through GPIOs if that's needed in your system. The power paths, the internal power paths are fully managed and fully protected, so they integrate both reverse current protection overcurrent protection, over voltage protection, and under voltage protection. On the other hand here, the TPS 65988 is very similar to the TPS 65987D, except it can support 2 ports, so 2 USB Type-C ports. With that, it's integrating both the ports, both the power paths as well in the chip. So one can be used to source and sink power on one port, the other can be used to source and sink power on the other port. Additionally, if more power paths are required, it also offers support for the external power path. Again, the internal VCON power paths are also optimized, and this is an optimized solution for dual port DRP power delivery applications. Here's a more in-depth look at the TPS 65987D. As mentioned, it has both of the power paths integrated. They're fully managed and can support up to 100 watts in either direction. The full USB PD modem is integrated into this device, so there's no need for an external microcontroller to control any of the PD communication. It's all integrated into the device. All the CC pin functions, such as cable detection and cable orientation, are performed by this device. Additionally, we offer the support for the legacy BC 1.2 protocol. This is so you can charge or be charged from legacy devices or legacy chargers. And there's a flexible system interface. So there's I2C slave and master ports. The slave port is so that you can use an external microcontroller to read back registers, debug registers, or change some of your configuration options during runtime. And the master port, the I2C master port, can be used to control external devices such as a SuperSpeed MUX or a battery charger IC. The TPS 65987 also has configurable GPIOs. So in case your slave devices cannot be controlled by I2C, you can use GPIOs to control those devices as well. So everything you need for a fully managed USB Type-C and PD port is integrated within this chip, and this chip can meet all of your USB Type-C and power delivery needs. So now we'll go into some more detail on one of our TI designs, one of our reference designs, using the TPS 65987D. This board here shows how easy it can be to create a power source only USB Type-C power delivery port. So this board here can support up to 100 watts, 20 volts at 5 amps. And with this, we used both power paths in the TPS 65987D and connected them in parallel to get a very low RDS-on solution. This is what we call power dual mode. So both of the internal power paths are attached in parallel, giving you half the RDS-on that the TPS 65987D would typically be. On this board, there's a variable DC to DC controller that is controlled through the GPIOs of the TPS 65987D. So whenever you make a new Type-C connection and you need to negotiate to the agreed upon voltage level based on the PD specification, the TPS 65987D will toggle the GPIOs to control that DC-DC supply and get the voltage to the right level. Additionally, if you want to manually change the voltages that are offered, there's some push button switches here which toggle GPIOs on the 65987D to change the voltage that you want to offer. So for example, if I click on this 15 volt button, then the TPS 65987D will offer 5 volts, 9 volts, and 15 volts, but it will not offer 20 volts. It will only offer the 20 volts after I've clicked on this 20 volt button. Again, this is all done through the internal PD modem inside the TPS 65987D, so there's no need for an external MCU to achieve this functionality. Here's a more in-depth look at this specific board. This is a system block diagram. You can see here that both of the back-to-back power paths are tied in parallel here to achieve the low RDS-on solution. The GPIOs are used to control the LM3489 variable DC to DC supply. And additionally here, you can see how the buttons are used to interface with the PD controller to change your offered voltage. Finally, this board takes a standard 20 volt barrel jack supply as an input, and it then generates all those voltages using the variable DC to DC supply. So this is a board that's very easy to get up and running. You just charge in your plug in your laptop charger, and you're good to go. This is the other side of the cable. So this is your sync side board. Again, this is done using the TPS65987D. This goes to show the flexibility of the device and the amount of configuration options that are available on the TPS65987D. Both of these boards use Wurth USB Type-C connectors. Additionally, and the TPS65987D is on both of these as well. Again, on this sync side, we also highlight the power duo feature, where both of the internal power paths are tied in parallel. Additionally, the buttons are also used here to control the sync power that you want to accept. So both these source boards and sync boards can also be used as handy debug tools in case you want to know, for example, what your off-the-shelf Type-C PD adapter can support. You can click through these buttons and see what the voltage negotiated on the Type-C contract can be. Here's a more in-depth look at the sync-only board. Again, you can see both power paths tied in parallel here to achieve that ultra-low RDS on. There's LEDs as well to highlight the negotiated voltage. Additionally, there's a push button here to control the voltage level that you want to support. Finally, there's some load test points here, so you can hook up an external load or attach this to an existing system to help convert it to USB Type-C and power delivery. Here's some test data that shows the benefit of going from a single power path to a dual power path. You can see here that when we're supporting a 20-volt 5-amp contract using a single power path, we have an effective RDS on of roughly 31 milliohms. On the other hand, if both of these power paths are tied together, we can support that same 20-volt 5-amp contract with almost half the RDS on as if we had the single power path. Although the Type-C PD spec does not allow for it, these power paths can support up to 20 volts at 10 amps. So doing that test, when we're just testing the internal power paths at 20 volts at 10 amps, we can see an effective RDS on of roughly 22 milliohms. As mentioned earlier, the TI power paths integrate the overcurrent protection as well as hard short protection. So you can see here when we're doing a 20 volt at 5 amp contract, you can see a large current spike here caused by a hard short, and immediately the VBus voltage drops down to ground to protect the system from this hard short event. Here's some more detail on all of the protections that are integrated into the TI power paths that are in the PD controllers. So first, there's over temperature shutdown. If the temperature on the board gets above a certain level, the PD controller will automatically disable the power paths and protect the system from any damage. There's also current limit. So if the current that's going through the power path is exceeding the negotiated level, the PD controller will either limit the current or open the power path to protect the rest of the system from either browning out the supply or drawing too much current from it. There's also under voltage lockout. So if the supply voltage drops below the threshold, then the switch will automatically open to protect against shorts and excessive current. Additionally, there's reverse current protection, and this is very important for USB Type-C and power delivery ports. Since you can both source and sync power on that same connector, there are conditions where current can go in the incorrect direction. So if, for example, you're negotiated to be a 5-volt source, but someone connects a non-compliant 20-volt source device to that, you need to make sure that the non-compliant 20 volts does not interfere with the rest of the system. Reverse current protection on the internal power paths helps prevent such events from happening. And then finally, there's also overvoltage protection on these power paths. This will also help prevent against non-compliant cases, or if there's some failure within the system causing the DC to DC to generate a voltage much higher that's expected. Again, the power path will open in these events, and the system will be protected from these non-compliant events. Here's a more in-depth look at how the TPS 65988 and 65987 implement the overcurrent protection. So initially, when VBus is first disconnected, Type-C is a cold connector. So if there's no connection, 0 volts is there. After a connection is made, VBus first goes to 5 volts. When VBus is at 5 volts, the TPS 65987 will implement overcurrent clamping. So this means that the current will be limited to the negotiated contract. So if you have a standard Type-C connection at 5 volts at 3 amps here, The current will not, through the power path, will not be able to exceed 3 amps. Additionally, we have a hardware over current protection that's meant to protect against hard shorts. When we have a 5-volt contract, this threshold is set at 10 amps. So if the current through the power path exceeds 10 amps, the switch will immediately open and protect the system. However, in the market, we know that there are some non-compliant sync devices that draw an excessive amount of current whenever they're negotiating a high voltage contract. So what that looks like is when you plug in your source device to some of these sync devices, we could see a very large inrush as the voltage on V-bus begins to increase. This large inrush current could sometimes be so high that it would trip the hardware over current protection. Now, a customer expectation is that a Type-C device will work with other Type-C devices no matter what the internal behavior is. So in order to work around some of these non-compliant devices, during a voltage transition from 5 volts to a high voltage, the TPS 65987D and 65988 will increase their hardware over current protection threshold to 20 amps just to let this inrush current pass through. Once we've reached a steady state and the voltage is at the new negotiated level, the hardware over current threshold will return to 10 amps and will begin measuring the current through the internal power path through a firmware OCP with a moving average filter. So if this moving average exceeds the negotiated contract for current, then the power path will open and protect the system from any dangerous events like this. So finally, I wanted to highlight some video tutorials that we have available that show how to implement a system with the USB Type-C and PD controllers that I covered today. These are very handy resources to look at and very good training videos to get a good understanding of how the TI Type-C and PD controllers work.
Thank you for joining us for today's Wurth Elektronik and Texas Instruments Power Seminar, USB Type-C and USB Power Delivery Made Easy. For questions, email us at here4you@we-online.com. That's here, the number 4, YOU, @we-online.com.